and thank you for joining in. Today we'll be starting with our first ever session on a series that will cover multiple research papers in the field of ML and AI. So, the whole process is that we'll go through a paper specifically in the field of AI, and then probably we'll give you code snippets of how to implement those research papers yourself and see them in action. So while we are at it, yeah, of course there'll be some improvements in the code along. Be feel free to reach out to us and we'll improve them with your help. If you have some interesting ideas about research papers that we should cover for you, most welcome to give interest in that as well. And yeah, the papers would not be right in the order. They might be of different fields, like we might cover reinforcement learning papers, machine learning papers, diffusion, and whatnot. But yeah, the paper would be around the AI specific topics. So I hope you learn from these research papers. You learn to how to read these papers, how to implement these papers, and hopefully you'll get something productive out of these. So let's just get started, and I'll just share my screen so that we can easily, yeah. So today we'll be covering this very interesting paper about solving the Lunar Lander problem under uncertainty using reinforcement learning. So those of you who are not much familiar about reinforcement learning, we'll just go through really basic terms of reinforcement learning and what it consists of, and then we'll go over to the problem, right? So as the abstract says itself, that reinforcement learning is an area of machine learning that is concerned with enabling an agent to navigate an environment with uncertainty in order to maximize some notion of cumulative long-term reward. So what's the basic idea of reinforcement learning is that you have an agent, consider it to be yourself. You have an environment, right? Let me just put it this way. So what it is exactly, say you have a agent, say it's me, right? Then you have an environment, right? Say a tree. Don't mind my bad drawing, but yeah, okay. So what exactly is reinforcement learning is whenever you have an agent in an environment, the agent wants to explore the environment, right? So even if we go to some new place, we want to explore that place, consider it that way. So whenever the agent reaches for the environment, it gets a certain state, say state 0. So environment initially gives the agent state 0, that is S0. So what it is, that agent approaches the environment, it senses the environment. Say the agent reached the tree and it found an apple. So that is state 0, right? Then the agent takes that state as 0, and based on that state, it does some action. It takes some action, say A. So I was in the environment, I am the agent, right? And I saw the environment, I saw the tree and the fruit, and my action was that I want to pluck that fruit, right? So I got there to near the tree and I plucked the fruit. Now I have the fruit, right? So this is my fruit, right? I have the fruit now, and that is a new state again. So S1, that is my reward. Sorry, not the state, that is my reward, right? So let's start again. The initially environment was in state S0. When I initialized, the agent explored in the starting. Agent saw an apple in the state S0 and it took an action A, that is to pluck that fruit. agent got the reward, the fruit as a reward from that environment that goes over here. Along with that, environment gave another state to the agent, that is S1. What is the state S1? Is the current state. So that current state might be that there was just one fruit on the tree and now there is currently no fruit at all on the tree, right? The fruit tree is empty. That would be the new state, that is the current state S1. So what the S0 becomes is the previous state, right? So how do we represent it in the field of RLS? According to her, we'll just say I'll take S0 as S now. That is the initial state or the current state when the agent started. Then it took some action A, it got some reward R, and it got into next state, that was S dash. So this is basically how the RL works, right? This is basically a queue function that we'll be talking next later in the paper. But this is actually the basic idea of what RL is. You have an agent, you have an environment. The environment initially you access its state, initial state. Based on that, the agent takes an action. Then it gets a reward for that action. The reward might be positive, might be negative. The agent might like throw a pebble on the tree. It might get a fruit, it might not get a fruit. That would be the reward. But after that, what happens in the sequence is the next state or becomes the current state of the agent, right? So let's just get back to the paper now. After this, in the paper only, we'll analyze two different RL techniques. So one of its algorithm is called SARSA. So SARSA is actually, the full form is actually the state, action, reward, state. This only is the full form of SARSA. And then deep Q learning is another, which makes use of deep neural network. And these are two algorithms that this paper will explore. So what is the problem over here? So problem over here is, as you are very familiar with the paper name, is a lunar lander problem. As the name suggests itself, that we want to land a lander on a surface, say on the moon surface. Of course it's lunar, right? On the lunar surface. So what we're going to do is, in the problem definition, we aim to solve the lunar lander environment in the OpenAI Gym kit using reinforcement learning methods. The environment simulates the situation where a lander needs to land at a specific location under low gravity conditions and has a well-defined physics engine implemented. So it's actually a combination of physics and computers, right? But the main aim or the goal of this problem would be that we want the agent to land on the landing pad as softly as possible and with as little fuel or maximum fuel efficiency as possible, right? So the state space is continuous, as in real physics. So the state keeps on changing, so it's continuous. But the action space is discrete. So we have a fixed number of actions that we can take in landing this lunar lander. So we have a continuous state space, so the state keeps on changing, but the action space remains discrete, right? We'll not go through the related work much, that it does not involve much interesting aspects. I'll move forward to just this figure. So it's very interesting figure. I just want to share something in this. So when we talk about the agent and the environment, I'm going to tell you that this lander is the agent over here for your reference only, right? And this whole black space and the landing part is the environment. And this is the landing pad. So initially what we want, that we want to land this lander in this place so that we get maximum reward, right? And this rest of the space, it's just, you'll get some reward, maybe you'll get negative reward, But for the agent to land safely on the landing pad, you have to land it in this maximum reward space, right? Next is the model framework. So model framework used for Lunar Lander Problem is the GIM toolkit. So GIM toolkit is actually given by OpenAI for developing and comparing reinforcement learning algorithms. So it has number of algorithms, like if you have heard of the Atari games or some of the latest advancements in robotics, it's very helpful so that you don't have to create a whole environment. It's already there for you in the kit. So the simulator we use here is the Box 2D, and the environment we use is the Lunar Lander V2. So there are a few versions of this, but I've used Lunar Lander V2 in the code as well. Right? Now, few things about RL. So we heard about the action space and the state space. What's the observations and the state space part? So observation space determines various attributes about the lander. So various observations about the lander, of course, and there are 8 variables that define the state space. So they are basically the coordinates of the lander, the y coordinates of the lander, the velocity, say horizontal velocity, vertical velocity, orientation theta, the angular velocity, and we have 2 Boolean states as well. So we have if the left leg is touching the ground or the right leg is touching the ground, right? So these are the 8 states. So let's just remember for that we have 8 states, and for the actions we'll come to the next part of that, right? So all the coordinate values are given relative to the landing pad instead of lower left corner of the window. The x coordinate of the lander is 0 when the lander is on the line connecting the center of the landing pad to the top of the screen. Therefore, it is positive on the right side of the screen and negative on the left side. So let me just go through this. It's not just that much important, but yeah, let's see this figure first. So what we have here is we have a naive SARS algorithm and we have a random algorithm, so like a random agent that intakes random inputs. So when we compare the rewards for these two is, see how many iterations, it took around 1000 iterations, and we see SARSA or naive SARSA is already working well, right? It's not trained on that and it's working well than a random agent. So we'll see how SARSA works when just we down here only, right? Yeah, and we back to the action space. So there are 4 discrete actions available. So we have 8 states and now we have 4 actions, right? So what are these 4 actions? 4 actions would be to do nothing, either fire the left orientation engine, either fire the right orientation engine, or fire the main engine. One thing to keep in mind is when you fire the left and the right engines, it introduces a torque. So that causes it to rotate and it's difficult to stabilize. What it means for us is that if we fire the left or the right engine, it will give us negative rewards. So let me just tell you what I mean by negative and positive rewards when I talk about rewards. So agent always gets a reward. It's like say there's an agent that's driving to the edge of the hill. So the positive reward would be that it detected that it's just the edge and it might fall down through the hill. So it moves to the different direction. It takes a round U-turn and moves in the different direction. So that is a positive reward. But at the same time, it could not understand that there was a hill edge and it fell down. That is negative reward because it won't be able to get past through it and return back, right? So that's the negative reward. So the agent needs to maintain both positive posture in the midair and reach the landing pad as quickly as possible. Of course, time is a factor here. So how we calculate the reward is, see, we have minus 100 into dt minus 1. So dt is actually the distance to the landing pad, while vt is the velocity of the agent, omega t is the angular velocity, and at time t and has landed is the reward function, right, of the landing, which is linear combination of Boolean state values representing whether the agent has landed softly on the landing pad. So it's all related to each other. With this reward function, we encourage the agent to lower its distance to the landing pad, decrease the speed to landing smoothly, and keep the angular velocity speed to the minimum to prevent rolling and not take off after landing again, right? So there are few things to keep in mind. If you want a reward from the agent, what you want to do is you want to lower the distance to the landing pad, decrease the speed so that you land softly, increase the decrease the time that you take to reach the landing pad, and of course keep the angular speed at minimum to prevent rolling. And all this done and you've landed, we don't want it to take off again, right? Next is the SARSA approach. So we have two approaches here. So what's the SARSA approach about? SARSA, we do not need to encode any prior knowledge about it, and SARSA seems to be a reasonable approach. It's an on policy algorithm, and it's use exploration policy. So SARSA is kind of a random policy. What it does is it takes random actions. SARSA is known for taking random actions, and what we meant by random actions is it's based on exploration. It explores a lot. It does not have any policy that's telling it in a defined way that you go this way, then you go this way, then you go this way. It's taking random actions, and based on the rewards it's getting back, it's taking time to just adjust to that, right? So the update rule for SARSA is given by this equation. It's a Q equation, Q value equation. You might not understand it right now, but yeah, after this one you will be able to understand a bit of it. So Q of st and comma a is a way to write the Q values given the state and the action taken, right? Here alpha this given is the learning rate, rt is the reward, Q of st plus 1 is the next state, Q value for next state given the next action, and st for the current state and the current action, right? You can see over here. So at any given state, you want the agent to choose an action that will give you the highest Q value corresponding to. And for that, what we do is we take argmax, right? So as I told you already, that SARS is an on policy algorithm, means that it does follow a given path only. It takes random actions. It follows a given policy that it thinks that it's right on. It's taking actions and getting rewards for that. It continues on that path and does not depend on any other policy, right? So a simple exploration policy is called the epsilon or the epsilon greedy policy, and where agent randomly chooses an actions with probability of epsilon and chooses the best action with probability 1 minus epsilon. Here it is. Alright, so a simple way of discretizing the state is to divide each continuous state variable into several discrete values. So why we do that is, why do we want to discretize this? Because we have a lot of data, but all that data is not of much use to us. So of course, when you look at this figure number 3, have a look at it. So what do you think? We have our landing pad. Sorry, so we have our landing pad just at this place, right? So it makes no meaning or no sense to try and land the lander at any of this other space, right? The space is of no use to us. We just want our lander to land at the padding, right? This place. So what happens is the states that are related to this place, the yellow portion, we are just concerned with that, and the rest of them would be generalized state. So what if that I have, like, say 10,000 or more states in the generalization area, and I turn everything to one, like I combine all those things and turn that to one state? Wouldn't that be much easier approach, right? So a simple way of discretizing the state is to divide it into each continuous state variable into several discrete values. However, as shown in figure 2, the result shows that the agent can only reach marginally better performance than a random agent, right? And can manage to get positive rewards even after 10,000 episodes. So it becomes obvious that we cannot simply adopt these algorithms out of the box. We have to tailor them so that we can use them for the Lunar Lander problem. So what is state discretization? We thought about that, okay, we'll just take all the states that are of no use to us and combine it into one. It's called state discretization, and what it consists of is that there are 5 continuous state variables and 2 booleans. Of course, 8 states we have, right? And so complexity of the state space is on the order of n to raise n power 5 crossed into 2 into 2, where n is the number of discretized values for each state variable, right? This even discretizing each state variable into 10 values can produce around 400,000 states. Now imagine that you have 400,000 states. What would be the compute cost? What would be the time that it will take for the agent to go through each and every state? And even most of the states would not be even useful for that agent. It would be sheer waste of time, right? So what we're going to do is, it explains the poor performance of that we were seeing previously, and therefore we need to devise a new discretization scheme for these states. So as a result, what we want to do is that we examine the initial Q values learned by the agent and observe that the agent wants to move to right when it's in the left half, or in the left half when it's on to right. So what we want to do, what it says is, say let me just take this one, right. Say the agent is in this space, this green one. So when it's in this space, it wants to move towards the next side, because going to this side is not a viable solution for it. And if the agent is here, then it would want to go in this direction rather than this direction, because it's again not viable for it, right? So what is the main aim here is that the agent wants to move to the right when it's in the left half space, and wants to move to the left half and the right half of the space, as a result of which x coordinates far from the center can be generalized into a single state. So all the coordinates that are outside of this boundary, these tiny dots, all the variables that are in this space, we can set them to a single state, right? That's what it says. We can generalize them into one. And how we do that is using discretization step, and the size is around 0.05, right? Next up is the exploration policy. So exploration policy is that how the state space size exceeds 10,000 even after doing the discretization process and generalization. So this greedy policy needs to be set to a fairly large number for the agent to explore most of the states, right? And however, this means that the agent will pick up suboptimal move once every 5 steps. So how we can minimize the performance impact of the greedy policy while still getting reasonable exploration is through epsilon decay. So what is epsilon decay basically? Epsilon decay is, we based on the number of iterations, say 0 to 100 and 100 to 500, we keep on decreasing the epsilon values, right? So that we get better performance on the greedy policy. Then is deep Q learning. As I already told you, deep Q learning makes use of deep neural network or a neural network, and its input is to a network is current state, say 8 dimensions of in our case, right? And the output are the Q values for state action pairs for that state. So Q values are actually the output for state action pairs for a given state, right? So it's given as Q of SA equals Q of SA plus alpha times, that is the learning times, into R rewards plus gamma maximum of the action that would be taken, q of s dash comma a dash, that is the next state and the next action, minus the current state and the current action, right? Also, then we find an optimal q value. So optimal q value is a value where the agent is said to converge. And what is meant by convergence is that when we reach a point where we can say that now the problem is solved, that is the point of convergence, right? So what we do in this whole part process is that optimal q value function q star is estimated using the neural network with parameter theta, and this has become a regression task. So the loss function at iteration I is obtained by the temporal difference error. So temporal difference is actually where it's a difference between what we think is the actual value and what the actual value or the reward is returned when taking a specific action. So it's the difference between the two. It's the difference between the actual and the expected, right? And based on that we have a loss function, and of course we know when we have a loss function we want to minimize it, and how the best algorithm to minimize it using gradient descent. So of course we use gradient descent to optimize the loss function and to update the neural network weights. The neural network parameters from the previous iteration theta I minus 1 are kept fixed while optimizing Li of theta I, right? But it's not done yet. We still have some of the problems here. The most important problem to face here is that we have successive samples that are highly correlated. And since the next state depends on the current state and current action, this is not a traditional supervised learning problem where the successive samples are actually IID, right? So how we tackle this is we make sure to store the encountered transitions by the agent into a replay memory. So what we do here is that any transitions that are encountered by the agent, we sample them into mini transition batches and we keep them into the replay memory. So wherever we want to train the network, we take mini batches from that transition memory and we use it to train the agent. To train the network. Of course, that's the agent only, right? So this technique is called experience replay. So you replay the whole experience again using a memory. In the code we call it a memory buffer, right? So another states, we have input layer. So we have states from S1 to S8. Then we have hidden layer. We have two hidden layers actually of 128 size, and then we have output layer and we get actions from A1 to A4, right? So let's see some of the experiments that they have conducted and what we can do about it. Right. So there are few of the experiments that they have done, and what these experiments are about is the original problem stays the same, that you want to actually land the lander softly with fuel efficiency as possible, and both lander legs should contact the lander surface much easily in the best possible quickly position and maintain the stable posture and the angular speed, right? And once the lander is landed, it does not take off. So but in this whole scenario, the lander is of course going to land on the surface of the moon because it's lunar lander. So there will be kind of some uncertainties, and we are going to talk about some of them. So say the noisy observations, right? So instead of directly getting the best of the purest observations, we do have some noise in the observation. So how do we face that uncertainty? So what we do is, instead of directly using the exact observations provided by the environment, we add a zero mean Gaussian noise of scale 0.05. And this scale is very important because we have the same discretization step size as well. So 0.05 is a discretization step, and also it is the same size for the scale of the Gaussian noise, right? I'll not go through these maths a lot because it makes this whole boring thing, But yeah, go ahead and read it through because it contains POM MDP, so it will take some time if you're really new to RL. So it will take some time to understand all these algorithms, but overview would be just great, right? Then there might be a random engine failure. That's also a kind of uncertainty. Another source of uncertainty is in the physical world is random force. So what happens that say there's a solar storm or the solar wind, like, right? So what happens for that, and how the lunar lander manages and gets fault tolerance prepared for itself so that it can handle any scenario or uncertainty like that. So we have some of the figures over here. So we can see that SARSA optimized went into got great results. So we reached around 115, around 10,000 iterations, and even the positive rewards were around, average positive rewards came around 2,000 iterations. But at the same time, a random agent or a naive SARSA agent could not do that well. It is in the negative rewards only, right? And at the same time, you can see the comparison of state discretization. So how much discretized the x coordinates were and the y coordinates were. So I guess the best results were for 5x and 4y, and I'll just read about it in the next part. So what were the analysis of the results of SARSA and the DQN? So figure 5 shows that was just above this one. Figure 5 shows that the average reward acquired by the random agent and SARSA agent with naive state discretization and a customized discretization scheme, and with the naive discretization which quantizes each state variable to 10 equal steps, the agent cannot learn about the outside environment very effectively even after 10,000 steps, right? We saw that. So it's the blue one in figure 5, right? And what it says then, that due to the huge state space, the acquired reward is only marginally better than the random agent. In contrast with our customized discretization scheme, which combines small step size discretization and large step size generalization, the agent is able to learn the Q values rapidly and gather the positive rewards after 500 episodes. So what it said is that normal naive SARSA and the random agent could not do that well, but in contrast to that, our customized discretization scheme did pretty well. Say it was a combination of small step size, but it was a combination of small step discretization and large step generalization, which led to gathering positive reward, or say converge, after just 500 episodes of training, right? It's cool, right? Then say the notation of AXPY is used to denote the x coordinate is discretized into A levels, and while the y coordinates are discretized into B levels. So for handling the noisy observations in figure 7, you can see say POM MDP worked pretty well. It is a enhanced version of RL or MDP if you know about it. And then vanilla Q did pretty well. It went into positives quite quickly, even after like 0 iterations it was there. And the plain Q started to do pretty well but could not reach there, right? Apart from that, there is one more thing, that is the random force. So what this random force handling is that after applying different random forces to the SARSA agent under state discretization of AX and 4Y, we have some random forces, say regular force, a medium force, and a large force. So the regular case, we ensure that random forces do not go beyond the engine power of the agent. So in the medium case, we tend to relax the constraint, and the large case, it totally goes out of its comfort zone. It's totally random, right? So it's not in control, I would say. So if you see figure 8 in this case, so in the large force, random force, we see in this dark green one, it does not go beyond 100 even, right? It's performing really bad on iterations, even 1000 iterations, right? For the medium one, it is doing pretty okay-ish work, but for the regular one, it did pretty good job, right? So it says that how the agent is trained or has explored itself against random forces. So done with that, we have how deep Q learning experiments were carried on. So for that, we have these number of neurons. So whenever we want to like play along with our deep neural networks, we usually play around the number of hidden neurons or the hidden layers, like increase, decrease, add or drop of layer, something on these lines, right? So what it did is see a difference over here. For a DQN, see that it all started in the negative range. See the peaks at the starting. These peaks actually tell you that agent is in the exploration phase. So whenever you see these peaks, it's obvious that the agent is exploring right now. It has nothing to do with the reward. It's just exploring the environment, right? And after that, you see the increase, and I think around, how about, say, let's just see over here. Let me just get this way. Say, for around 100 iterations, our 128 hidden neuron DQN did pretty well. It was the first one to cross in a 100 iteration. It crossed the zero barrier for average rewards, right? So it did pretty well on that. And at start, the average reward is highly negative since the agent is essentially exploring, as I told you. And at that time, it's collecting more transitions and storing them into the memory, because of course we are accessing that memory and we are experiencing that replay from the memory buffer, right? As the agent learns, the Q values start to converge. The agent is able to get positive average rewards, right? Then how it handles the random engine failure. Trained DQN agent performs well on the new environment with random engine failures and is able to obtain positive average rewards of around 100 plus, even after when without retraining, and the original agent is able to just adjust to the uncertainty. So if we see about this figure 10, we see that DQN 128, we see these along, right? Just still learning and training. But for a trained DQN, see how the spike was not here. The spike started from this place and it was already in the positive and it continued like this. Even though the 128 in DQN was able to surpass it at this point, but you can see that a trained DQN performed much better, right? And even if the agent would not fail, it will do much better in the green one. But in the usual everyday scenario, engine failure could be possible. So the blue line did pretty well, not that bad and not that well, right? So what's the conclusion about this paper is that we observed that how SARSA and DQN agents performed for the Lunar Lander one, and we have seen that SARSA is able to handle the random forces, right, while the DQN agent is able to handle the engine failures quite well. However, retrained SARSA was failing to handle the noisy observations, and it's totally understandable that it will take the agent some time and iterations to get that fault tolerance in itself. And yeah, it comes from training, it comes for hyperparameter tuning and everything. And that is what I'll just show you. The next is how this code works. Let me just go ahead and stop the mirroring of the screen and take you to the code. Let me just reconnect this. So I've already run this whole for you, but I'm gonna rerun this. Okay, so yeah, let's just go ahead and just connect this and be done with. So this is the whole notebook. I'll provide you the link for that. So as I told you already, we need the PyBox 2D for library for just working and installing the environment. So it's just environment setup. We have the open we have the OpenAI and everything, right? So just let me just go ahead and clone this repository. It helps to actually work with the environment pretty well, and this whole setting of the environment actually takes some time, and it might be a little tricky process, but don't worry about it. It will be done in no time, right? So let me just go ahead. Yeah, so see, once the installation is done and everything is done, then we have to import the gym environment, and after that we want to import numpy, random, all these imports that are required. We're using pytorch over here, and for collections tq and name tuple, and I'll let you know what the use of it is. But before that, how to set up the environment. So it takes environment name and seed. So what I did was I called the gym, that is OpenAI gym dot make, and passed in the environment name, right? It sets up the whole environment for me. Then I set the seed, and I print the state shape and the action shape, right? So it returns me that for the state we have 8 states, and for the action we have 4 actions, right? And if it was not, then we have of course the exception errors. Then let's just see everything, because we're gonna work on the neural network. We have our DQN class. So what we're gonna do in the DQN class is we take linear layers, as we saw in the diagram. We use leaky relu for that, and we make our whole DQN. It's a pretty small network, so you don't have to be really strict on yourself and just work around the number of layers. I use 64 here, try 120 in your own, like do everything. Yeah, then it's the GPU check. We're using CUDA. We have CUDA, so right, if you don't, just use the CPU. Then memory management, we were talking about experience replay, class buffer memory buffer that we want to use so that we can keep the transitions and the transactions handy and give it to the neural network so that we can be trained on the past references, right? So we have memory replay memory here. We use DQ for that and pass in the buffer size. We have the experience tuple, so it takes in the current state, the action, the reward, the next state, and the done flag, right? Just 5 of them. Then we update the memory, of course. For every experience that we have to update the memory. We sample from the memory because we have a batch size. We sample in form of mini batches, so we batch that, and of course after doing all this work and converting from numpy to torch and torch to numpy, all those things done, we return the current state, actions, rewards, and next states, and the done flag, right? After you're done with this, I think I've run this, let me just run that again. After you're done with this, let's just define our agent. So agent takes in our DQ network, our memory buffer, number of states, number of actions, seed, and the learning rate, right? After we have the DQN setup, we want the loss function, and we have the loss function, we want an optimizer for that, and we want a criteria, that is MSC loss, so for the loss function, right? So what we're going to do is we take a Q target that comes from the environment. Then we have an expected Q that comes from the local network, and what we do is that we use self.criteria, that is MSE loss, and then we optimize it. We have the optimizer Adam. Then once it's done, we update the weights, right? Once all of this is done, we get the scores. So we want to know what's the average score or the average reward for the agent that we have trained on. So we use usually around 2000 samples, 2000 episodes, and the epsilon value start from 1.0, and we want the epsilon decay to be applied, so we use a decrement of 0.995. Once that is done, and we have a check value over here that is around 200. So what the check value means is that for this particular situation, what it is that 200 is said to be a reward. When we have a reward value of 200, the problem is said to be solved, just for this one, for the Lunar Lander one. It said that if you have an average reward of 200, the problem is said to be solved, right? So once we have reached that, we just print out the average score and check for the value, and we pass it the number of states, that is 8, number of actions, that is 4, seed value of 42, and the learning rate of 0.01, right? So let me just go ahead and run it. But you can see for yourself from my previous run that it actually converged at around 628 episodes to solve with average score of 200.01, right? So while it's running, I'll just show you a few of the plots that I've already done before, right? So I was plotting for episode and score. So I got, you can see the scores were initially negative when I started for around like 100 episodes or so, but after 100 episodes there was a spike ahead, and I got around pretty good, around 150 I got the first positive score. So it's not the best plot, I would say, but yeah, it is pretty good to say that we were, after each and each episode iteration, we were reaching for a better score, right? So how for each episode the epsilon value was decaying, you can see in this one. Then there's a scatter plot for this, right? So we see here that epsilon values, the way they were if they were decreasing, the score was quite better than for a large epsilon value of around 1, right? And I also ran it for like 100 consecutive episodes. For what I was doing in the previous one was I ran it for like 100 episode batches, but what I'm doing here is I'm just running for it for 100 episodes, right? Consecutive episodes. So you can see the timeline has changed over here as compared to the previous one. So for the episodes, you see these spikes are more spikier, right? Average score came out to be like 217. That is pretty good, I guess, right? So once that is all done, what I did was I took a video snapshot of that as well. So for that, what I did was I used gym.rappers.monitoring, and I imported the video recorder right from that, and OS as well. So what I did was I took the agent, the trained agent, this one. So I called the agent name and passed in everything, right? I took the trained agent, I took the environment and passed to display model video. So what it does, it actually creates a whole video for the lunar lander, and it is actually trained on the neural network that you train for yourself. So this whole code is actually about implementation of DQ, and you have not implemented SASA, feel free to go ahead and do that. But if you want to implement a DQN, make sure you make some changes in hyperparameters as well. So I have a video that I already ran and just show you that as well. But if you want to experiment a bit more with that, so you can go ahead and experiment the gamma values, you can experiment with some epsilon values, like try different epsilon values, or maybe the learning rates. So try and change the learning rates for DQN and it will work for you in different ways. Though I have to warn you that it will take some time for it, but yeah, it's worth it then, right? But I'll just go ahead and show you the lunar lander video, right? So here is the video of what I trained previously, and see how the lunar lander comes down in speed and then it makes it right in between the two poles. So it gets a positive reward of about 200. And you want to see that again, that it was quite fast coming down, but it actually slowed down when it reached this position, that around this position it slowed down because it was near, and it actually calculated the distance, then it reached down quite smoothly and soft landing, right? So that was it for that. And just go ahead and try this code for yourself, get better scores than this one. Try different scores, try different values, maybe try different hyperparameters, try Sasha algorithm on this one, make DQN better, maybe try some other algorithm that you find interesting yourself. And yeah, if you have any improvements to this one, do reach out to us, and I hope that I see you again for the next paper reading session as well. So thank you so much for joining in.